At this very moment, something unimaginable is happening to you. Invisible, untouchable, and completely undetectable, countless streams of dark energy are passing straight through your body. Not once, not twice, but an almost incomprehensible number of times every second. Scientists estimate that this happens around 10 to the 28th power times per second. To put that into perspective, that number is far greater than the total number of stars in the entire observable universe. And yet, you feel nothing. Your body isn't torn apart, you're not affected in any noticeable way. So what exactly is this mysterious force? If it's powerful enough to influence the entire universe, why does it leave you completely unharmed? Is dark energy real, or is it just a theoretical illusion created by scientists? And if it didn't exist at all, what would happen to the universe? Hello, Earthling. Today, we're going to explore one of the greatest mysteries in modern science, dark energy, a key piece in understanding the origin and fate of the universe. Now, you might be thinking, if something can't be seen, touched, or directly detected, how is it any different from myths or superstition? That's a fair question, and it highlights the fundamental difference between mysticism and science. Mysticism makes claims, science makes claims, and then demands proof. Dark energy wasn't invented out of imagination. It emerged from one of the most shocking discoveries in the history of astronomy. In 1998, two independent teams of scientists set out to answer a seemingly simple question: how fast is the universe expanding? Using powerful space telescopes, including the famous Hubble Space Telescope, they observed distant galaxies deep in the cosmos. At the time, everyone believed they already knew the answer. Since gravity pulls matter together, the expansion of the universe, set in motion by the Big Bang, should be slowing down over time. Eventually, it might even stop in reverse, causing the universe to collapse back in on itself. That was the expectation, but what they found instead changed everything. The universe isn't slowing down, it's speeding up. Not only is space expanding, but the rate of expansion is increasing over time. Gravity, the force that binds galaxies, stars, and planets, is simply not strong enough to stop it. Something else, something far more powerful on cosmic scales, is pushing the universe outward. This unknown force doesn't emit light, it produces no heat, it cannot be seen or directly measured, and yet it appears to control the fate of the entire cosmos. This is what we call dark energy. Today, dark energy is one of the greatest unsolved mysteries in physics. It isn't matter, it isn't radiation. Even its cousin, dark matter, is easier to understand. Scientists have never directly detected dark energy. Instead, its existence is inferred from its effects, specifically the accelerating expansion of the universe. Observations suggest that over the past 5 billion years, the universe has essentially stepped on the gas, expanding faster and faster. If only normal matter and dark matter existed, gravity should have slowed everything down by now. But the opposite is happening. This means there must be a force working against gravity, a kind of cosmic repulsion. You can think of dark energy as a tension built into space itself. On small scales, it's incredibly weak. In a volume as large as the Earth, the total amount of dark energy is comparable to just a single grain of sand. That's why in our everyday environment, on Earth, within the solar system, or even across our galaxy, its effects are completely overshadowed by gravity. But dark energy has one crucial property: it exists everywhere. It fills the vast emptiness between galaxies. And when you scale up to the size of the entire universe, those tiny effects begin to add up. Over billions of light years, they accumulate into a force strong enough to stretch the fabric of space itself. Based on current estimates, the volume of the universe roughly doubles roughly 10 billion years, and an overwhelming portion of that expansion, nearly 90%, is driven by dark energy. This raises an even bigger question: where is the universe heading? Even Albert Einstein once struggled with this problem. When he developed the theory of general relativity in 1915, he believed the universe was static, unchanging, and eternal. But his equations told a different story. If the universe contained matter, gravity would eventually cause it to collapse. To fix this, Einstein introduced a term into his equations in 1917, the cosmic logical constant, represented by the Greek letter lambda. This term acted like a repulsive force, balancing gravity and keeping the universe stable. But later discoveries proved that assumption wrong. In 1929, astronomer Edwin Hubble made a groundbreaking observation. Galaxies are moving away from us, and not randomly. The farther a galaxy is, the faster it's receding. This relationship became known as the Hubble law. But the real revelation was even deeper. It's not that galaxies are flying through space, it's that space itself is expanding. Imagine the surface of a balloon. As the balloon inflates, points on its surface move away from each other, not because they're moving on their own, but because the surface itself is stretching. Galaxies behave the same way. They are like tiny points on the surface of a cosmic balloon. As space expands, the distance between galaxies increases. This expansion is described by a value known as the Hubble constant, which measures how fast space is stretching. On average, for every 3.2 million light-years of distance, the expansion speed increases by about 72 kilometers per second. That might not sound like much, but here's the key. It adds up. A galaxy twice as far away recedes twice as fast, 10 times farther, 10 times faster. At extreme distances, galaxies appear to move away faster than the speed of light. But this doesn't violate physics, because it's not the galaxies themselves moving through space faster than light. It's space itself expanding. A good analogy is a moving walkway at an airport. You could stand still, but the ground beneath you carries you forward. Similarly, galaxies aren't racing through space. Space is carrying them apart. However, not everything is affected equally. On smaller scales, gravity still dominates. For example, our galaxy, the Milky Way, and its neighbor, the Andromeda Galaxy, are gravitationally bound. Instead of drifting apart, they're actually moving towards each other and are expected to collide in about 4 billion years. So here's the big picture. On local scales, gravity wins, but on the largest scales imaginable, dark energy dominates, driving the universe into an ever faster expansion. And that brings us to a critical question. If the universe is expanding, how do we know for sure? What evidence do we actually have?
If the universe is expanding, how do we actually know? What proof do we have that space itself is stretching? The answer lies in something as subtle and as powerful as light. When light travels across the universe, it doesn't move through empty, static space. It moves through space that is constantly expanding, and that expansion leaves a signature. Light behaves like a wave. Every wave has a wavelength and a frequency, and those properties determine its color and energy. When distant stars or galaxies emit light, that light begins an incredibly long journey across the cosmos. But as it travels, the space it moves through is stretching, and as space stretches, so do the waves of light. This stretching increases the wavelength and lowers the energy of the light. For visible light, that means something very specific. It shifts toward the red end of the spectrum. This effect is known as redshift. The farther light travels, the more space it crosses, and the more space expands during that journey, the more the light is stretched. So when astronomers observe distant galaxies, they see something remarkable. The farther away a galaxy is, the more its light is redshifted. This gives scientists a powerful tool. By measuring how much a galaxy's light has shifted toward red, they can determine how much the universe has expanded since that light was emitted. In other words, redshift allows us to look back in time and track the history of cosmic expansion. But there's a problem. Not all galaxies are reliable markers. They vary wildly in brightness, size, and structure. To measure distances accurately, scientists need something more precise, something consistent, something that acts like a cosmic measuring stick. Astronomers call this a standard candle, an object whose true brightness is known. If you know how bright something really is, and you measure how dim it appears, you can calculate how far away it must be. But what in the universe is bright enough, consistent enough, and visible across billions of light years? The answer comes from one of the most violent events in the cosmos: supernova explosions. When certain stars die, they explode in spectacular fashion, releasing enormous amounts of energy in a brief flash. But not all supernovae are useful. Many vary too much in brightness to serve as reliable measurements. There is, however, one special type, Type 1a supernovae. These explosions follow a very specific rule. They occur in binary star systems, where two stars orbit each other. One of those stars is a white dwarf, the dense core left behind after a sun-like star exhausts its fuel. On its own, a white dwarf is stable. It can exist quietly for trillions of years. But if it has a companion star nearby, something dramatic can happen. The white dwarf begins to pull matter from its partner, slowly gaining mass, and as it grows heavier, it becomes increasingly unstable. Eventually, it reaches a critical limit, a precise threshold known as the Chandrasekhar limit, about 1.44 times the mass of our Sun. At that exact point, the white dwarf can no longer support itself. In an instant, it undergoes a runaway nuclear explosion. The result is a Type 1a supernova, an explosion so bright it can briefly outshine an entire galaxy. But here's the key. Because these explosions always occur at nearly the same mass, they also produce nearly the same peak brightness. That makes them perfect standard candles. No matter where they occur in the universe, their intrinsic brightness is almost identical. So by observing how bright they appear from Earth, astronomers can calculate their distance with remarkable accuracy. This method opened a new window into the cosmos. For the first time, scientists could measure distances across billions of light years and compare those distances with redshift data. This allowed them to reconstruct how the universe has expanded over time. And that brings us back to one of the most important moments in modern science, the year 1998. Two independent teams of astronomers set out to map the expansion of the universe using Type 1a supernovae. Their goal was simple: determine whether the expansion was slowing down under gravity or not. At first, everything seemed to confirm expectations. In the early universe, expansion did appear to be slowing down. Gravity was doing its job. But when they looked deeper, farther back in time, at more distant supernovae, they saw something completely unexpected. Those distant explosions were dimmer than they should have been. Not just slightly dimmer, but significantly. And there was only one explanation that made sense. The universe in the past was smaller than predicted, which means the expansion of the universe didn't slow down, it sped up. Sometime around 5 billion years ago, something changed. A new force began to dominate the cosmos, a force powerful enough to overcome gravity itself. That force is what we now call dark energy. This discovery reshaped our entire understanding of the universe. It revealed that gravity, the force that binds galaxies and forms stars, is not the ultimate ruler of the cosmos. On the largest scales, something else is in control. Today, scientists describe the universe using the LACDM model, the standard model of cosmology. And according to this model, everything we see, stars, planets, galaxies, and even ourselves, makes up only a tiny fraction of reality. Roughly, 4% is ordinary matter, 23% is dark matter, and a staggering 73% is dark energy. That means nearly 3/4 of the universe is made of something we don't understand, something invisible, something that is driving the expansion of space itself. And perhaps most astonishing of all, we are living in the era when dark energy has taken over. The fate of the universe is no longer determined by stars or galaxies, but by this mysterious force that fills the void between them.
In 1998, something extraordinary happened in the world of science. Two independent research teams were racing toward the same goal, to understand the true fate of the universe. One was the Supernova Cosmology Project, led by Saul Perlmutter. The other was the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Both teams were using the same cosmic tool. Type 1a supernovae, the brightest and most reliable standard candles in the universe. Their mission was simple, yet profound: to measure how the expansion of the universe is changing over time. At the time, scientists believed they already knew the answer. It was widely accepted that after the Big Bang, the universe expanded rapidly. But over time, gravity, driven by all matter and dark matter, should have been slowing it down. Like a thrown ball losing speed as it rises, the universe was expected to decelerate. Eventually, many believed, expansion would slow, stop, and possibly reverse into a collapse, a dramatic big crunch. That was the dominant picture of the cosmos. But the universe had something unexpected in store. As both teams carefully analyzed distant supernovae, they first looked at relatively nearby cosmic history. And at that scale, everything seemed to make sense. The universe was slowing down in its earlier stages. Between roughly 4 and 8 billion years after the Big Bang, gravity appeared to be doing exactly what it should, pulling the expansion back. The data matched expectations. For a moment, it looked like science had confirmed the standard model. But then they looked further, much further. They turned their attention to extremely distant supernovae, events so far away that their light had traveled for billions of years before reaching Earth. These weren't just distant objects, they were time machines, showing the universe as it was in its deep past. And what they found changed everything. The most distant supernovae were not behaving as expected. They were dimmer than they should have been, fainter than the models predicted. And in cosmology, faintness is not just a detail, it is a clue. It means distance is being misinterpreted. And if distance is wrong, then our entire understanding of cosmic expansion must be wrong. After careful analysis, both teams arrived at the same shocking conclusion. The universe was not slowing down, it was accelerating. This meant something profound. At some point in the history of the universe, roughly 5 billion years ago, the expansion stopped decelerating and began speeding up. Instead of gravity winning over time, something else took control. A new, invisible influence began pushing space outward. This was completely unexpected, because gravity, matter, and dark matter should have been slowing everything down, but instead, the universe was doing the opposite. It was stepping on the gas. So what could possibly cause this acceleration? What kind of force could overcome gravity on the largest scales in existence? The answer was unknown, but scientists gave it a name: dark energy. That same year, 1998, a landmark scientific paper reintroduced an old idea from Einstein's equations, a term he once added and later abandoned, called the cosmological constant, L. Originally, Einstein had introduced it to force the universe to remain static because he believed the universe was unchanging. But after Hubble's discovery of cosmic expansion, Einstein called it his greatest mistake. Now, ironically, that mistake had returned as the leading explanation for the accelerating universe.
Dark energy was not just an abstract idea anymore. It became part of the new standard model of cosmology, a framework scientists now call LCDM. In this model, the universe is divided into three major components. Only about 4% is everything we can see and touch: atoms, stars, planets, galaxies, and all ordinary matter. Around 23% is dark matter, an invisible substance that holds galaxies together through gravity. And the remaining 73%, the largest portion by far, is dark energy. This means that everything humans have ever observed, studied, or experienced directly makes up less than 1/20th of the universe. The rest is invisible and mostly unknown. Even more striking is what this implies. Dark energy is not a small correction or minor effect. It is the dominant force shaping the universe today. It determines how fast space expands. It influences how galaxies drift apart, and ultimately, it controls the fate of everything that exists. From about 5 billion years ago until today, dark energy has been steadily increasing its influence. Before that, gravity dominated the universe, but now the balance has shifted. We are living in the dark energy-dominated era of cosmic history. And in this era, something strange is happening. Galaxies are no longer simply responding to gravity. Instead, the fabric of space itself is stretching faster and faster. Not because galaxies are moving through space, but because space itself is expanding between them. This discovery fundamentally changed how we understand reality. The universe is not static, it is not slowing down, and it is not controlled solely by gravity. Instead, it is a dynamic system shaped by an invisible energy that fills all of space. And yet, despite its enormous influence, dark energy remains one of the greatest mysteries in physics. We cannot directly detect it. We do not know what it is made of, and we do not know why it exists. We only see its effect, the accelerating expansion of the cosmos. But this single effect is enough to rewrite our understanding of the universe. It tells us that the universe is not just evolving, it is accelerating into an unknown future, a future that depends entirely on the nature of dark energy. And that is still something we are trying to understand. At this point, one thing is clear. We are no longer living in a universe where gravity alone determines destiny. Something deeper, something invisible is in control, and we are only beginning to uncover its secrets.
Even after the discovery of dark energy, scientists were left with a critical question. How do we prove something we cannot see, touch, or directly measure? If dark energy truly fills the universe, then there must be subtle traces of its influence hidden in cosmic history. So researchers turned to two powerful tools, both indirect, both incredibly precise. The first tool is called Baryon Acoustic Oscillations, or BAO. At first glance, it sounds complex, but its idea is beautifully simple. BAO is essentially a fossil imprint of sound waves from the early universe, a frozen memory of when the cosmos was still young, hot, and chaotic. To understand this, we must travel back to the beginning. In the early universe, everything was a dense, glowing plasma, a mixture of particles and radiation tightly bound together. Matter and light were constantly interacting. Gravity tried to pull matter together, forming clumps of density, but radiation pressure pushed back, resisting compression. This constant struggle created ripples, like sound waves traveling through a cosmic fluid. These were not sound waves in air, but pressure waves in the early universe itself. They spread outward, shaping regions of slightly higher and lower density. And as the universe expanded and cooled, something dramatic happened. About 380,000 years after the Big Bang, atoms finally formed, light was released for the first time, and the universe became transparent. At that moment, those sound waves were suddenly frozen into place,
locked into the structure of the cosmos forever. What remains today is not sound, but structure, subtle patterns in how galaxies are distributed across space. These patterns preserve the imprint of those ancient waves, like ripples left behind in frozen water. This is the essence of baryon acoustic oscillations. They act as a cosmic ruler built into the universe itself, a fixed scale that scientists can use to measure how the universe has expanded over billions of years. By comparing the size of this standard ruler in the early universe with its size today, scientists can track how space has stretched over time. And when they do this carefully, they find something striking. The universe today is stretched more than expected, not just slightly, but significantly. And the only explanation that fits the data is the presence of a force accelerating expansion. That force is dark energy. But BAO is not the only window into the past. There is another, even older source of information, a kind of photograph of the infant universe. This is the cosmic microwave background, or CMB. It is the oldest light in the universe, a faint glow left over from the Big Bang itself. To imagine it, think of the universe as a newborn. For the first 380,000 years, it was so hot and dense that light could not travel freely. The universe was opaque, like a thick fog of particles and radiation. But as it expanded and cooled, atoms formed. Suddenly, light was able to move freely for the first time. That ancient light has been traveling ever since, and today it fills the entire universe as a faint microwave glow. This is the universe's baby picture, captured when the cosmos was just 380,000 years old. And thanks to satellites like COBE, WAMAP, and the Planck mission, we can now study it in incredible detail. What these missions revealed is astonishing. The cosmic microwave background is not perfectly uniform. It contains tiny fluctuations in temperature, slight variations in density and energy. Some regions are a little warmer, others slightly colder. But these differences are incredibly important because they represent the first seeds of all structure in the universe. Those tiny ripples eventually grew under gravity. Over billions of years, they formed galaxies, clusters, and the vast cosmic web we see today. In a sense, every galaxy, including our own Milky Way, was born from these tiny fluctuations. These fluctuations are also deeply connected to the same physics that produced baryon acoustic oscillations. They are different stages of the same cosmic process, sound waves and density waves frozen across time. Together, they form a consistent picture of how the universe evolved, and most importantly, they give us a powerful way to test dark energy. Because both BAO and the cosmic microwave background act like measuring tools written into the fabric of the universe itself. They allow scientists to compare the early universe with the present one, and when those measurements don't match simple gravity-based predictions, something extra must be acting on cosmic scales. That something is dark energy. The conclusion is becoming increasingly difficult to avoid. The universe is not expanding at a constant rate, it is accelerating. And this acceleration is written into both the large-scale structure of galaxies and the faint glow of the universe's oldest light. So now, we are faced with an even deeper realization. Dark energy is not just a hypothesis supported by one observation. It appears in multiple independent lines of evidence. Supernova measurements, galaxy distribution patterns, and the cosmic microwave background all point towards the same conclusion. Something is driving space itself apart. And yet, despite all this evidence, we still do not know what dark energy actually is. We can measure its effects, we can map its influence, we can describe its role in cosmic history, but its true nature remains hidden. It is as if the universe is telling us, I am expanding faster, but I will not yet reveal why. And so the story continues. Scientists now have a cosmic ruler, a baby photograph of the universe, and a growing set of precise measurements, all pointing towards one undeniable fact. The universe is being pushed apart by something we do not understand, something invisible,
something everywhere, something we call dark energy. And with that, we reach a new question. If dark energy is shaping the expansion of the universe today, what will it do to the future of everything that exists?
If dark energy is truly shaping the expansion of the universe today, then one question becomes unavoidable. What will it do to the future of everything that exists? To answer this, scientists are now preparing their most powerful tools ever built. A new generation of space telescopes is being sent into orbit, each one designed to measure the universe with unprecedented precision. Leading the effort is the James Webb Space Telescope, a powerful observatory designed to look deeper into space and further back in time than anything before it. It is helping us see the earliest galaxies, the first stars, and the structure of the young universe. Alongside it is the European Space Agency's Euclid mission, specifically designed to study dark matter and dark energy. Its goal is not just to observe galaxies, but to map how the universe expands across billions of light years. And in the near future, NASA will launch another revolutionary mission, the Nancy Grace Roman Space Telescope. Named after one of the pioneers of space astronomy, it will become one of the most powerful instruments ever built for studying cosmic expansion. Together, these three observatories form a new scientific alliance, a global effort to solve the greatest mystery in cosmology. Their mission focuses on one crucial number, the equation of state parameter of dark energy, usually written as W. This tiny number holds enormous power because it determines how dark energy behaves, and ultimately, it determines the fate of the universe itself. If W equals -1, then dark energy is constant. It would mean space itself carries a fixed energy density, unchanging over time. This matches Einstein's cosmological constant, and under this scenario, the universe would continue expanding forever, slowly growing colder and darker. But if W is slightly greater than -1, something very different happens. This is the idea of quintessence. In this case, dark energy is not constant, it evolves over time. It could slowly weaken as the universe expands. This means the acceleration of the universe might change in the distant future. In this model, dark energy is not a fixed property of space, but a dynamic field, possibly even a new fundamental force. This idea opens a completely new possibility, that dark energy is not just a constant background, but something alive in the evolution of the cosmos, a fifth component of nature, beyond gravity, electromagnetism, and nuclear forces. But there is another, more extreme possibility. If W is less than -1, the universe enters a far more dramatic scenario. This is known as the phantom energy. In this case, dark energy doesn't remain stable, it grows stronger over time. The expansion of the universe doesn't just continue, it accelerates uncontrollably. A runaway effect begins. As space expands, dark energy becomes even stronger, which causes even faster expansion. A feedback loop is created, and the universe begins to tear itself apart. This leads to one of the most dramatic theoretical endings in physics, the Big Rip. In this scenario, the timeline of destruction unfolds like this. First, galaxy clusters break apart. Then, individual galaxies lose their structure. Stars drift away from each other. Planetary systems become unstable. Even the Milky Way would eventually disintegrate. As time continues, the destruction moves inward. Planets are pulled away from their orbits. Moons separate from their planets. Even Earth would be pulled apart by the fabric of space. In the final stages, nothing remains bound. Atoms themselves begin to break apart. Electrons are torn away from nuclei. Even atomic nuclei are destroyed. Matter as we know it ceases to exist. At the very end, space-time itself is stretched beyond its limits. Distances between particles become infinite.
every structure in the universe is pulled apart until nothing remains connected. The universe ends not in fire, not in ice, but in a complete and irreversible tearing of reality. But despite its dramatic nature, most physicists believe this scenario is unlikely. It requires conditions that may violate fundamental principles of physics. So while it is mathematically possible, it is not the most accepted outcome. The more widely accepted future of the universe is far quieter, but far longer. It is known as the heat death of the universe. In this scenario, the universe continues expanding forever. Galaxies drift farther and farther apart. Star formation slowly stops as gas is used up. Existing stars eventually burn out. The night sky becomes darker over time. Black holes remain for unimaginable periods, slowly evaporating through Hawking radiation. Even they eventually disappear. In the far future, all energy becomes evenly spread out. No temperature differences remain. No usable energy exists. No structure can form. The universe becomes a vast, cold, dark, and silent expanse, a state of perfect equilibrium where nothing ever happens again. This process is so slow that it unfolds over timescales of around 10 to the 100 years, or even longer, far beyond anything we can truly comprehend. But even now, the story is not finished, because new telescopes are already collecting data. The James Webb Space Telescope, Euclid mission, and future observatories are steadily improving our understanding of dark energy. Each new observation brings us closer to answering one of the deepest questions in science. What is driving the expansion of the universe? Is dark energy a constant property of space? Is it a changing field? Or is it something entirely unknown, something beyond current physics? At the moment, we do not know, but we are closer than ever before. And so we return to the ultimate question. What is the fate of the universe? Will it expand forever into a cold, silent emptiness, or will it tear itself apart in a final cosmic rupture? For now, the answer is still hidden, but the universe is slowly revealing its secrets, one observation at a time, one discovery at a time, until one day we finally understand the force that controls everything. And perhaps then we will finally know whether the universe is gently fading into darkness or racing towards its ultimate destruction.